Hello, hello, hello. Are you able to hear me?
Yes, sir.
So if you are okay, now are you able to hear me? Please respond, someone. Hello, 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 hello.
कुछ रेस्पॉन्स नहीं आ रहा।
Hello, 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 hello.
मेरी आवाज नहीं, उधर से उनकी आवाज सुनाई दे रही।
Hello, 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 hello.
नहीं, ये तो मैं फोन से बोल रहा हूँ।
Hello, 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 hello,
सुनाई दे रहा है।
hello, 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 hello.
मैं कंटिन्यू करता हूँ क्योंकि वो उधर वो जो
Hello,
बैठे हैं ना, वो कांटेक्ट कर रहे हैं। नोबडी इज रेस्पॉन्डिंग।
hello.
अच्छा, तो कोई वो नहीं करेगा। तो अभी मैं बोलता हूँ, फिर बता देना, मेरे फोन पर बता देना कि मेरी आवाज आ रही है नहीं आ रही। ठीक है। अच्छा, करेक्ट।
Hello.
आप चालू करो कि उधर आवाज आ रही है, लेकिन किसने बोला था कि आवाज नहीं आ रही? क्या चक्कर है?
Hello, hello, hello. एक बार पूछो।
इस पे बताएगा वो। हेलो हेलो, मतलब वो
हाँ, बोलिए।
स्टूडेंट जो
हेलो, हाँ
पार्टिसिपेंट
सर।
है ना, उनके लिए अंडू कर दिया है, तो नोबडी इज
सुनाई
रिस्पॉन्डिंग।
दे रहा है आपका
अभी
आवाज।
किसी ने रिस्पॉन्स किया था सर।
किया था।
हाँ,
हेलो।
भैया अच्छा अब बोलिए, इसी के माइक्रोफोन से डायरेक्ट कनेक्टेड होगा।
चलो आप ट्रांसपेरेंसी।
यस, हेलो हेलो।
हेलो,
हाँ सर, सुनाई दे रहा है। आप इस प्रेजेंटेशन शेयर कीजिए ना, बात प्रेजेंटेशन दीजिए सर।
हाँ, लो इस
हेलो।
फोन पे बात कराऊं।
की जा रही है क्या आवाज? हाँ सर, मैं ज्वाइन किया हूँ सर। हाँ, ठीक है सर। ठीक है।
हेलो,
हाँ सर,
Now you
आवाज
can
आ
ask.
रही है आपको?
आ
हेलो।
रही है?
जी
आवाज आ
सर,
रही है?
आवाज आ रही है सर। यस सर, यस
ठीक है,
सर।
okay.
नाउ यू विजिबल सर।
You know that the system may be described higher order, any system in the form of higher order differential equations, which may be expressed in the form of either a transfer function or a first order set of first order differential equations, which we know the state space representation of the system. There are many high order systems, just like in power system engineering, multi-machine power system with synchronous governor, prime mover, and exciter. This is high order system. Similarly, in chemical engineering, the multi-component column is also a high order system. The analysis of all such systems is difficult, tedious, requires more hardware and computational efforts. Therefore, it is not neither cost effective nor it can be further it poses challenges to the for the implementation. Therefore, it is desirable that the higher order system must be replaced by a lower order system that is the higher order system in some sense. Most of the available model order reduction systems, model order reduction methods, they are available in the literature. They may give the reduced order model either in the form of transfer function form, or they start with a state space model. The transfer function model give the reduced order model in the same form, that is in the form of the reduced transfer function. Similarly, the state space model also give the model a reduced order state space model. Why we use what is the necessity of model order reduction? To have better understanding of the system, to reduce computational complexity, to reduce hardware complexity, to generalize results established on a particular system to comparable system, to improve the methodology of the computer-aided control system design. And these are some of the applications of the reduced order modeling, that is prediction of the transient response sensitivity, prediction of dynamic errors, control system design, adaptive control system using low order model, designing reduced order estimators, suboptimal control, provides guidelines for online interactive modeling. What is the model reduction problem? Let us take the system is described by the higher order transfer function. That is GS is equal to, this is B0 plus B1s plus B2s square plus Bm s to the power m, A0 plus A divided by A0 plus A1s plus A2s square. This is the high order description of the system. This is another order transfer function. Or alternatively, the higher order system may be described in the form of state equation, which is given in equation number 2. That is x dot is equal to axt plus bx ut, y is equal to cxt. In case of the transfer functions, these models, that is GS is C Si minus A inverse B. The two representation, that is transfer function and the state space, they are related by this equation. In case of the transfer function reduction methods, RS is the reduced model. It is a Rth order model, which is given by as the ratio of the two polynomials E0 plus E1s plus E2s square plus EP s to the power m upon D0 plus D1s plus D2s square plus drs to the power n. Here R is the order of the reduced order system. Similarly, in the state space form, the reduced order model is given by equation 4, that is xr dot is equal to AR xr plus BR ut, YRT is equal to CR XR. YRT is the response of the reduced order system, whereas YT was the response of the higher order system. There are different model reduction methods, which may be broadly classified. I told you in the beginning in two categories, that is time domain reduction techniques and the frequency domain reduction techniques. This presentation will be represented only, will be confined to the model reduction for the transfer function models, transfer functions, high order system. That is frequency domain methods. In time domain, these are the main approaches: model analysis approach, subspace projection method, optimal order reduction, balance realization method, singular perturbation method, balance residualization method, aggregation method, Hankel matrix approach, and Hankel non-approximate method. These are the, I have named some of the methods in time domain simplification methods. Then there are frequency domain reduction techniques, which are made as given, that is continual fraction expansion and truncation, Parde approximate techniques, moment matching method, matching frequency response, Routh stability criterion method, stability equation method, Mihailov stability criterion method, error minimization method, dominant pole retention, polynomial differential method, polynomial truncation method, factor division method. These are the main frequency domain reduction methods. Now we will take up one by one. Before that, frequency domain reduction method, because this presentation is confined to the frequency domain reduction methods mainly. They can be divided into 4 basic categories. When the classical reduction methods, which I call CRM, and the algebraic methods such as time momentum matching method, Parde approximation method, continuous fraction method, truncation method. There are 2 drawbacks of these CRM, classical reduction methods. The reduced order model obtained by CRM may be unstable, although the high original system is stable. The second disadvantage is the low accuracy in the mid and high frequency ranges. Then second category in the frequency domain reduction method is the stability criterion method, SCM. These methods include Routh approximation method, Routh-Hurwitz array method, stability equation method, Mihailov criterion method, Hurwitz polynomial approximation. They use one of the, actually these methods, they use one of the criterion and always leads to the, they use the stability criteria, some of the, and always give the stable reduced total mole for the stable system. Then third category is stability preservation method, SPM. This include dominant pole retention method, factor division method, truncation method, differentiation method. They also give stable models, but do not use any stability criteria. The fourth category is mixed reduction methods. They use combined features of both SCM and CRM, in which the denominator of reduced order model is found by SCM and the numerator is determined by CRM. The absolute stability of MRM is achieved at the cost of serious loss of accuracy, because this is the mixture of the two methods. Then in the classical reduction methods, first one is the continued fraction method. The higher order transfer function is described in the form of GS, which is a higher order transfer function of nth order. So it can be expressed either in the core first form. This is 1 by H1s, H2s, H3s, H4s, and so on. So the H1, H2, these are the quotients of the first cover form. Then GS is given like this transfer function, the ratio of the total transfer function, A1, H2, n minus 1. This nth order system, with the help of the coefficient of this system, we prepare the Routh array, which is given below, A11, A12, etc., and so on. And the criteria for developing this table is given where Aj minus 2, K plus 1 is equal to Ajk, Aj minus 1, Aj minus 1, K plus 1 upon Aj minus 1. So the all the coefficients H1, H2, they are determined by this algorithm. So in the continued fraction method, if we use this Routh, construct the Routh array for this third order system, that is 360 plus 171 plus 10s square upon 720 plus 702s plus 71s square plus q. So from the coefficients of this transfer function, that is the denominator, we construct this table, Routh array. And these coefficients are obtained by taking the ratio of the first two columns, that is 1 by 10, 10 by 20, and so this 58.9 and so on. So this basically, we have the H1, H2, H3 quotients of the first cover form. The first cover form, this is the model obtained by the first cover form method as given by the third order system reduced to second order system. In this case, you see that if you see the output, there is a steady state error. So that is this advantage of this method. Then cover second form. In this case, we have the coefficient H1, H2, H3, H4, etc. Again, they are determined by forming the Routh array and by using the generalized criteria Ajk is equal to Aj minus 2 K plus 1 minus Aj minus 2 1 Aj minus K plus 1 upon Aj minus 1, where J is equal to 3, 4, and so on, and K is equal to 1, 2, etc. Hj, that is the quotient of the second cover form, are determined by this method. The rth order reduced model is obtained by taking 2r Hi quotients and matching the coefficient of, that is by matching the coefficient of the cover second form. This example is taken again third order system. There H1, H2, H3 are computed by the above Routh algorithm, and then after truncating with certain terms, we get the second order model. You can see that the steady state error SSE is 0 in this case, whereas in the first cover form there was steady state error. Then the cover third form is, in this case, both the quotients H1, H2, H3, capital H2, small h3, these are the quotients. They are determined by this generalized Routh algorithm. H1, H2, H3 from left side, ratio of the left side, and the H2, H4, etc. from the coefficients of the right hand side. Then this generalized algorithm is used for determining Hj and Hj. If you can see that if all capital H are 0, the equation reduced to the cover second form. If small all H are 0, then the equation reduces to the cover first form. Again, this advantage of this method is that there is no steady state error because both H1 and capital H are used in this case. So this same third order system taken and this step response is computed, which is showing 0 steady state error. Then cover modified form. This is, in this case, we have the quotients H1, H2, H1, K1, H2, K2, etc. They are obtained with this algorithm, which where H1 is given A11 by B1, H2, and so on. And using this generalized algorithm, we can find out Hj and Kj, that is Aj1 by Bj1, Kj, Bj, and plus 1 minus j. This they are used to find out the quotients of this core modified form. In this case, we have taken a eighth order system, and a second order model which is given by 18s plus 5.436 upon s square plus 7.7s. And the response of the first higher order system and reducer system is closely matching. You can see there is no error. The second method in this category, first category, is time moment matching method. This time moment GS is expanded like this: 0 to infinity gt e to the minus st dt. If you expand e to minus in the form of exponential, we have 1 minus st plus, and by multiplying with this gt, we have the various time moments. These gt, dt, gt and tgt, they are denoted by c0, c1, c2, or in general ci s to the power j. So ci is computed by like this. So ti is known as the time moment of the system. On the other hand, if numerator and denominator term of the transfer function are arranged in the descending order, then gs is given by mi s to the power minus I or ca I minus 1b. In fact, these two are the methods to give the Markov parameters. This is, you can say that if you expand the transfer function by about s is equal to infinity, you get the Markov parameter. If you expand it by about s is equal to 0, you get the time moments. If the ABC are given, then you can use the formula C a to the power I minus 1 into B. These are the various Markov parameters and time moments. This time moment matching technique is equivalent to the continued fraction expansion approach. Now I am telling you how to find out the time moment. This is the high order system GS. The coefficients of numerator and denominator are arranged in the ascending power of s. Then by dividing, you can get C0 plus C1 as C2. These are the time moments. In fact, they are time moment proportionals, but we vaguely say them time moments because they serve the same purpose. By division algorithm, you can obtain Ci. GS is this one. Then Rauthian array is compared like this. Then performing by computing these matrices C1, C2, A1, A2 are C1, C2 is equal to this, AI, A1 by this. Then C11 is given by this whole matrix. And with the all three matrices, you can get the various time moments. This is the third order system. In the third order system, that is approximated for this R2S like this, A21 plus A11. That is a second order model is obtained. The poles of the system and the original system, they are almost close. And this is the step response of the original system with the reduced order model. You can see that the step response is matching with that of the original system. The third method in that category is Pardai approximation method. In the Pardai approximation method, the given transfer function GS is expanded about s is equal to 0. giving C0 plus C1 S square plus C2 S square. The Padai approximant is nothing than a rational function equation PNS by QMS, PMS by QNS, and this rational function is equated this above power series. That is C0 plus C1S, and with the by comparison you can get these type of the equations A0 B0 C1, A1 B0 C1 plus B1 C0 and so on. By solving these equations, the coefficients of the reduced order model are obtained. In matrix form, you can get the time moments with these equations. This is a high order system, sixth order system. If you compute the R2S and R2S by taking the different closed loop poles, so we are getting these three kth reduced order models. This method, that is Padai approximation, have four basic drawbacks. The reduced order model may be unstable, stable, although the operant system is stable. The Padai approximant often shows non-minimum phase characteristic. Non-minimum phase means the zeros are lying in the right half of the S-plane. The reduced model often shows the poor matching in the transient zone. The steady state values are same as that of the high order system. The third method is the factor division method for model reduction. In this case, this is the system GS given by this. So the denominator is factored like this. SP1, let us assuming that poles are real. Then by dividing the S plus Pnth pole into the numerator, you can get n minus 1th order transfer function, which is given by Gn minus 1 as below. Similarly, if you divide it by another factor, you get n minus 2th order model and so on. This is the factor division method. By using this, you can find out the reduced order model. This is the algorithm for computing another method, advanced method of factor division method. In this case, alpha method parameters and in some case beta parameters are determined to obtain the reduced order model by factor division method. This factor division method can be extended to other method. That is, you can take that GKS, you can put like this NS by DS, and GS is then written like this. And by computing D hat S and DS this, you can generate the various models. This is the fourth order system. In the fourth order system, you have determined the second order model by factor division method, and you can see the response of the second order system. Again, the steady state is matching because the time moments are alternatively matched, and the response of the original reduced system is very close. That was in the factor division addition of the alpha parameters. Now, so you can use the addition of the beta parameters in the factor division method. And this GS is the fifth order system given, for which alpha parameters are given alpha 0, alpha 1, alpha 2. Similarly, beta parameters are given here. By taking various combination of alpha and beta, that give you the various time moments matching. That is t is equal to 0, m is equal to 0. That is 0 Markov parameter, 3 time moments. You are getting this reduced model. If you take m1, t2, then you get this type of reduced model. If m is equal to 2, t is equal to 1, you get this type of reduced model. This step response of all these three models is compared with the reducer system that is given like this. So that was these three methods, that is the continued fraction method, Padai approximation, time moment matching method, factor division method in the first category. In the second category, we have the stability criterion methods. In the stability criterion, the first method, let us take Routh approximation method. This is, you can see GS either by direct method you can obtain Rx, or GS is first inverted to get G cap S, and then from this R cap S, again, you can get the reduced order model. This, in fact, this Routh approximation method require two types of inverse transformation. That is, given system is first inverted, and then the reduced order, after obtaining the reduced order, again it is inverted, then you finally get the reduced order model RKS from the second side. So these are the main steps which I told you. First, we find out the reciprocal of the full order system. Then we construct the alpha beta tables, obtain kth reduced order model by RKS. Then we reciprocate RKS to get RKS. These are the four steps used in Routh approximation method. In the Routh approximation method, we need to construct two tables. One is alpha table, which is obtained from the denominator coefficients. This is the alpha table, which is constructed by well-known Routh approximation method. And this is beta table. This is obtained from the numerator coefficient, and the part that is A01 is numerator, B0 is denominator. Similarly, this one. So these beta parameters are determined. Using alpha beta parameters, then we get these equations N1S, D1S, that is for first order system, N2S, D2S for second order system, and 3 D3 for third order system. This is the given system expanded in the alpha parameters, that is alpha coefficients are there, and DRS is obtained like this by truncating that continued fraction expense. This is D1S is 1 plus alpha 1S, D2S. These are the reduced order denominators of the given system obtained by that is alpha table from which we have constructed in the Routh approximation method. Then the second method in this category is the Hurwitz polynomial approximation method. Here DS is expressed GS square plus HS square. That is the GS square is given by this polynomial, HS square given by this. That is even and odd terms, in fact. And then HX by GX is obtained by this type of continued fraction. And the reduced HX by G plus X is obtained by truncating this continued fraction extension. We have taken a sixth order system in this case to illustrate this method. So this is the sixth order denominator. From this is a sixth order system whose common denominator is s to the power 6, 41 s cube, 57, 571 s to the power 4, and so on. This is the sixth order system. First is reciprocal is taken, that is d hat s. Then time moments are computed for the original system, like, and Markov parameters like this. ds is given by this, and ds s square plus hs square given by this for the sixth order system. This so alpha, for constructing the alpha beta parameter, for finding the alpha beta parameters, we construct this table. From this alpha 0, beta 0, alpha 1, beta, etc. All these coefficients are found. And then reduced model is given by D2S, S square plus 1.548, 2678S, and so on. In time domain, you can say this is the second order model, which is given here, XR like this. And this is the second order transfer function. Second order denominator using the Hurwitz polynomial approximation. These are the step responses of the original and reduced system for the four outputs. Then second method is Routh-Hurwitz array method. In the Routh approximation method, we need to construct alpha and beta tables. In this case, in the Routh-Hurwitz array method, we don't construct this table. Directly from the given transfer function GS, you can obtain RS by first a table is constructed, Routh table is constructed from the coefficients of the denominator polynomial alpha table. Similarly, this is numerator stability array from a denominator coefficient, from numerator coefficient. And then this table is from the denominator coefficient. By taking the first two rows of these tables, you can have the original system. If you take the second two rows of both the tables, you can get another first n minus one other reduced order and so on. So directly from by constructing the Routh array, you can find out the various reduced order models. You already know how to construct the Routh table. That is, first two rows are written from the coefficients. Then there is this set algorithm, which the third and subsequent arrays are generated, which is given below. Then third method in the stability criterion method is the stability equation method. GS is given this. GS is that is NS by DS or BM S to the power M, BM minus S to M, and so on. And here numerator, so from the numerator and denominator, the even and odd terms are separated. They are written like this. And NES BI S to the power I, then NOS BAI S to the power I. These are the numerator stability array, stability equations. So by neglecting the higher order factors from these, you can find out the reduced numerator as well as reduced denominator. So this is DES given by A0 plus A2 S square with the even terms, and DOS given by A1S plus A3S, that another term. These polynomials are factored like this, DES and DOS. These are the stability equations. Then you can neglect some of the factors, higher order factors from the stability equation to get the reduced numerator stability array and the reduced denominator stability array. And the reduced order model is finally constructed as given by RS from these reduced stability equations. Then another method in this category is Mihailov stability criterion. In this case, DS S is replaced by J omega. Then this is factored. That is, the even and odd terms are separated in two polynomials, phi omega and psi omega. Where omega is the angular frequency. So after that, you can construct a Mihailov characteristics. That is, DRS is then obtained by epsilon omega and j eta omega, where epsilon omega is given by this equation, eta omega is given by this equation. Sorry. And finally, epsilon omega is given by lambda 1 omega square, omega 1 square, these factors. Similarly, eta omega is given by lambda 2 omega square, omega 2 square, and so on, these vectors. And finally, by truncating the sum terms, you can get the reduced form. Another method is the differentiation method. In the differentiation method, in fact, this method was proposed by Gutmann. In this case, numerator and denominator are successively differentiated to get the reduced order numerator or denominator. The reduced order denominator, in fact, in the differentiation method, we don't directly differentiate the given polynomial. We first take its reciprocal, then differentiate it, and again, after combining the reduced numerator and reduced denominator, we get the reduced order model. The third method in this category is the truncation method. Truncation method is nothing, is simplest method. Given a from the given transfer function, you can truncate the terms from the numerator and denominator directly to get the reduced order model. We need not to do any algorithm of. So differentiation and truncation method, these are very simple. हाँ चलो मंगवा दो थोड़ा. Now हाँ दे दो थोड़ा.
यही रख देता हूँ, आपको लेना.
ठीक है. Now let us come to the combined methods or mixed reduction method. We have discussed some methods, that is the stability criterion method, which preserve the stability, and we have discussed the classical method, just like continued fraction, Pardee approximation, and so on. So those methods are combined with the stability reduction methods. The classical reduction method are combined with the stability equation method to obtain the reduced order method. First one, let us take Pardee approximation and model method. That is, you by dominant polar tension, you define the denominator, and by using the Pardee approximation, you find out the numerator coefficients. Now, Pardee approximation using Raoult stability criterion. In this method, you can use the Raoult stability criterion for finding the denominator and the numerator by Pardee approximation method. Similarly, Pardee approximation by Raoult-Hurwitz array. In this case, again, the denominator you can obtain by Raoult-Hurwitz array and the numerator by Pardee approximation method. Or factor division of Mihailov stability criterion method can also be used for combining these methods. Mixed method using these first four are the using the Pardee approximation method. Pardee approximation method combined with the stability criterion methods. Then you can also obtain the mixed method by using the continued fraction expansion. You know the continued fraction first cohort form, second cohort form, third cohort form, and the modified cohort form. Those all the forms you can use to construct the numerator, and the denominator you can find out by those stable reduction methods. Okay, the procedure is same. Find out the denominator by those methods, stable reduction method, and numerator by the four forms, that is the first, second, third, and modified cohort form of the continued fraction method. So that give a nice combination of the combined method of reduced order model using continued fraction and the stable reduction methods. Pardee approximation and dominant pole retention. We have illustrated this, that is which I told you just now. So these are the dominant poles. Pardee approximation obtained first GSE expanded by C0 plus C1 as C2 as square, where the CI coefficients are given by this algorithm. And numerator terms are obtained by solving these Pardee equations. That is, first for finding the denominator, then you can write down the Pardee equations to get the reduced order model. By solving these equations, you can find out the reduced order model. So Pardee model method, that is simple, retains the dominant poles of the system and find the zero of the reduced order model by Pardee approximation method. Now, so far we have assumed that the dominant poles are written, or of the system are obtained. That is, just by factorization you can find out the dominant poles. But these are the dominant pole may also be written by either of the following methods. By finding the roots of the characteristic equation, that is one way. The poles nearer to the imaginary axis are the dominant poles. By finding the residue corresponding to the various poles. The poles corresponding to large magnitude radius are the dominant poles. or there is a Koenig's theorem is also there, which can also be used to find out the dominant poles. This is a sixth order system. You can see the coefficients, how large these coefficients are. From this sixth order system, the poles of the system are given here, -1, -1, -10, -10, -100, -100. And using Pade approximation, you have determined the denominator. That is, denominator is determined by the dominant poles and the numerator by Pade approximation method. This is third order model obtained by in the same technique. And these are the step responses of original and reduced systems. The reduction of multivariable system also carried out by the same method. In this case, in the numerator, you have the matrices just like A0, A1, AK -1. And the reduced order model is obtained by using these equations. This is the x dot equal to ax plus bu, y equal to cx plus du. From this, you can find out first the characteristic equation, and then using the formula which I told you earlier, you can find out C0, C1, etc. Now, let us discuss the stable reduced order Pade approximate using Routh-Hurwitz array. In the Routh-Hurwitz array method, you know that you need to construct the numerator and denominator stability arrays. From those stability arrays, you can find out the numerator and denominator directly. But here we are mixing it with the Pade approximation. So instead of going to the numerator, we first reduce the denominator and obtain the reduced denominator by this method. And then by using the part of GSE expanded in the form of C0 plus C1s plus C2s square, by equating the Pade approximate in which the denominator is already known, the other coefficients may be determined of the reduced order model. So any polynomial of kth order model is constructed like this. This is generalized form of this one, and the RK is obtained like this. This third order system is given here, which is expanded about s is equal to 0 in terms of 1 plus 0.5s plus 0.75s square minus 3.375s cube and so on. From these coefficients of the denominator, we construct the Routh array. And denominator is obtained by taking the second two rows S2 and S to the S1 row. D2S is obtained finally. Once D2S is obtained, the numerator terms are obtained by Pade approximation method. What is the contribution of time moments and Markov parameters in reduced order modeling? The time moments are used to match the steady state of the system, whereas the Markov parameters are used to match the transient response of the system. The time moments, you can know how to determine the time moments. One, see directly by division, you can obtain the time moments. And Markov parameters, you can directly obtain by division by expanding the given transfer function about s is equal to infinity. So this is a third order system which has been expanded into this power series, and the first second order model is obtained by Pade approximation method. This is the fourth order system, in which again a second order model is obtained by balanced truncation method, and this is the step response of the original and reduced system compared. Again, we have taken an example of higher order system which is expanded in terms of the Markov parameters, and then the step response are shown here for this original and third and fourth order system. In order to determine reduced order models by matching time moments and Markov parameter, the desired reduced order model must be stable. Only time moments are sufficient for determining the reduced order model, and its time response, both transient as well as steady state, will match with the response of original system. The time moments can be used for matching the transient response of the original and reduced models. So you have seen that first we have discussed the classical reduction method, then we discussed the stable reduction method, then we have discussed the combined reduction methods. Now we are discussing the combination of those methods with the help of the intelligent techniques. You know the intelligent techniques just like GA and PSO. There are many other also GA and other than genetic algorithm, particle swarm optimization. There are other intelligent techniques also. So what procedure is how to use these intelligent techniques for finding the reduced order model. So first we find out the denominator of reduced order model by stable reduction methods, which can be obtained by dominant pole attention method, Raoult approximation method, Raoult array method, stability equation method, differentiation method, Mayalo stability criterion method, truncation method. So with the help of these, we can find out the denominator. Then determine the numerator by error minimization using genetic algorithm. In the genetic algorithm, you can obtain J or JSE 0 to infinity yt minus of rt, this is transient response error. Then compute the unit step response of original and reduced systems and match the steady state values. This gives one unknown coefficient of the numerator. Compute the integral square error like this, that is J is equal to ISE 0 to infinity yt minus rt. This error index is function of the unknown numerator coefficients, which are determined by minimization of J using GA, or you can use the other intelligent technique, that is the particle swarm optimization technique. Also, you can use for finding for minimizing this error. The basic algorithm used in the GAR, there are initialization. We can generate the initial population and binary with strings and depends on the precision required. Then evaluate the fitness function, which I told you that is the error yt minus rt 0 to infinity. Then we apply the genetic operators, that is crossover, mutation, and reproduction, to obtain the best fitness value. Then second and third steps are repeated to get the desired reduced order model with desired accuracy. This is the flowchart for implementing the GA as follows. There is initialization of the population, evaluate this function, error function at t is equal to 1, then stopping, apply stopping criteria. If answer is no, then mutation, crossover, reproduction. These operators are applied, otherwise stop. In time domain and frequency domain, mainly we are concentrated on the frequency domain method. We have discussed the various method of frequency domain method. Then we have also discussed the combination of these classical reduction method with intelligent techniques and the combined reduction method using the Pada approximation, continued reflection, and moment matching, etc., by stable reduction methods. So that those are the basically some of the frequency domain reduction methods. There are others also, male method I have covered. Now let us discuss the problem of the controller design problem. In this case, the uncontrolled plant is represented by GPS. It is desired to design a controller GCS such that when the loops are closed, the unity feedback system is stable and has and desired response. Sorry. Suppose the high order plant is given by GPS has poor dynamic characteristics such as high overshoot or high oscillatory response of step with step input. It is required to find a controller such that frequency and time response of the control system, GCL, closed loop system, with original system, and with that those of the reduced order model, RCL, match closely. So this is the GPS and GCS in the forward loop, forward path of this loop, and GCS and RPS and GRS are the corresponding reduced system, that reduced system. So if the performance of GP is not good, then we are putting a controller in the loop such that when the loop is closed, the response is satisfactory and have the desired response. That is the, in fact, the controller design problem. So MS, the third block in this third diagram I have shown MS. MS is equivalent open loop transfer function corresponding to the given closed loop. So GCL, the closed loop transfer function is given by GCS and GPS plus upon 1 plus GCS plus GPS. Similarly, closed loop transfer function with the second figure, you can say RCL, GCS, RPS, 1 plus GCS, RPS. So we have designed a PID controller using this approach. In fact, any rational type of controller can be designed. We have illustrated with the help of the PID controller. So this is the PID controller. The first block, which I represented, is GCS, that consists of KP, and that is these three coefficients, that is KP, KV, and S. And JP is the plant transfer function. So GCS given by, let us design the PID controller. GCS is given by KP plus K1 by S, KDS plus KDS. And for designing the PID controller using reduced model, a reference model MS is required. Reference model MS, it is a closed loop system in fact. So M hat S is the, that is system obtained from the given original system as the open equivalent open loop transfer function. Then the equation PID controller design, you use this equation, GCS GS is equal to M hat S. M hat S is compared with this, and the coefficients of KP, KI, and KD are determined. If you want to find out the closed loop system, what is given by GCL, that is given by GCS GS plus GCS plus GS. Now let us take an example. This is a high order system, and M hat S, MS is the open loop closed loop system, or reference. You can say this MS is the reference model, which is determined from the by using the response of the system, closed loop system. Then from MS we obtain M hat S, which is given by MS by 1 minus MS. That is a equivalent open loop system corresponding to given system. Then GCS is expressed as M hat S by GS, which is set equal to E0 plus E1S E2 S square 1 S. And then these, by comparing these two, right hand side, we can find out the K0, Kp, and Kv of the given system. Once these are obtained, the reduced form obtained by Prober method is like this, and GCL is like this. That is the closed loop transfer function M hat by RS. So in this case, we have compared the step response with the reference model. And then here we have another compensator design we have carried out. This, in the earlier example, we have taken a PID controller as the GCS. Now we have taken GCS as K plus 1 plus K1 as that irrational function. So, and this MS is the same. That is, MS is the reference model. From MS, M hat S is obtained like this, MS by 1 minus MS. Then GCS, GPS, this equation is compared with M hat S. So finally, the coefficient of GCS are this rational controller are obtained like this. And here MS is given by this. And this is another example I have taken. Fourth order system is given. And for this, MS is taken like this. This is obtained from the specification of the given system. The open loop reference model is obtained like this, M hat S, MS by 1 minus MS. By using the original system, the PID controller is obtained as follows. And this rational controller is obtained. Here in this case, we have compared the various model reduction methods which are used for compensator design. Then, yes, that's all. So what we have discussed in this talk? We have discussed first, what is the model reduction problem? We have defined the model reduction problem in time domain and frequency domain. Then we have discussed the various, we have just named the time domain reduction methods. Then we have discussed the frequency domain reduction method in length. After that, we have combined the frequency. We have obtained the combined or mixed reduction method by using stable reduction method and the techniques such as continued fraction expansion, Parde approximation, and so on. Then we have combined these model reduction method with the intelligent techniques. So this way, a brief introduction of the various, or you can say brief overview of the methods of model reduction is given, and the research are still carried out in this direction. So that's what I want to share with you. Okay. And these are some of the important references I have used to frame this talk. You can take these, or you can, with the help of these references, you can find out many other. So now I must thank you, most of you methods, for listening these various topics, various methods in the model reduction area and the controller design problem, in which we have described only a PID controller and a rational controller. 2 examples have been taken. So that's all which I wanted to share to you. Hello?
Sir. So, yeah, any doubts
Hello?
from the participant side?
Hello?
Yes, sir. You are audible. If you have any question, please kindly unmute yourself, please.
Please. Hello?
I
Yes,
think
sir, you are audible.
no one.
So
Sir, I
please
think
put
there
your
is no
query.
question, sir.
Hello?
Hello.
Sir, so I think no one is having any doubts. So thank you so much, sir, for sharing your valuable talk with us, and our participant definitely benefited with your fundamental knowledge on the model order reduction, sir. And
Okay.
yeah, so really it is grateful for you giving your time, valuable time with us and from your busy schedule, sir. So thank you so much, sir. So now we are closing the sessions, and all the
Right.
participants are requested to join tomorrow.
If
Thank
these
you.
participants wants this lecture, the printout of this lecture, I can send it.
Okay, sir. Okay.
So I will forward it to you.
Yes, sir. Yes, sir.
You can give this lecture to your participants. Okay.
Okay, sir. Okay, sir. Okay. So thank you, sir. Thank you so much, sir.
Okay.
Okay, thank you, sir.
Okay. Thank you very much.